All right, cool. So, picking up from where we left off, the last couple of lectures have been on different kinds of neural network architectures, and we're still in the sort of supervised domain. And this week, we're going to start talking about unsupervised learning in the lecture after this that kind of complements this. And I kind of was torn about whether or not to include recurrent neural networks in sort of the topics that we cover. But given that we've largely been building this base of understanding of machine learning, and this is sort of in a way superficial, right? Because many classes or courses on this stuff will go really deep into implementing these things, and this is more of a seminar topics course, so we're going to touch on a lot of these topics, and hopefully you all can go and explore these things deeper as you discover them, or you've already been exposed to them to some amount. But I think that it'd be remiss not to include the recurrent neural network architecture, or sort of this idea of recurrently applying a neural network algorithm in the general context of how to apply deep learning algorithms. This is sort of important in that, in a way, you could even argue that all neural networks are recurrent. It's almost a bit of a superficial, as you'll see in this lecture, this idea of recurrently, or using a neural network architecture and applying it multiple times over the same data and kind of creating these sort of conditional dependencies between each stage. It is largely a sort of way to think about how we're applying neural networks to a particular problem, and less of a architecture choice. But I think it exposes a different way to think about solving certain problems, especially problems that we haven't seen yet, such as when you have, say, one output and many inputs, or an arbitrary number of inputs and one output, or any kind of combination of the two. So recurrent neural networks are really kind of, in that context, important to consider, and have seen a lot of success in particular natural language processing, which we'll talk about a little bit in this lecture, but also just in general as a framework to think about how you can perhaps approach different kinds of problems. And in this context, recurrent neural networks, or RNNs, don't really add much new stuff to our existing toolkit or tool belt, or however you want to think about it. They're more of a sort of example of how to apply neural networks in a new way versus kind of the things that we've seen thus far. So kind of let's dive into it, and this week we'll also talk about unsupervised learning and start to explore that as well, which will lead us into sort of the next segment of the course on unsupervised learning, and we'll spend a lot of time in unsupervised learning over the next couple of weeks in terms of implicit models for generative type of things, as well as some reinforcement learning too. So that's going to be fun. But yeah, let's dive into it. So, okay. So far, the tasks that we've been looking at have been bound, as in, I give you an image of a cat, and the result of that is a classifier that tells me that this is a cat, and here's the bounding box that tells me this is the space in which the cat occupies in the image. We didn't really go deep into computer vision models like Mask RCNN, which is able to do or any kind of region proposal network. So I'm not talking about that here. There are ways to apply the neural networks that we've seen to sort of deal with more complex scenes and such. But the kind of core idea here is that these are not arbitrary outputs, as in we have an image and we expect a sort of set output from that. Even in the semantic segmentation case we talked about, or the multiple object detection case, we're really splitting the problem down. We're kind of divide and conquering the problem, and what we're interested in are more unbound type of scenarios. For example, and this is sort of a common example where you see recurrent neural networks, is trying to create some kind of caption or a description of an image. For example, this on the bottom left, you have an image, and the description is a living room with a couch and a television. The middle one is a man riding a bike on a beach, which is clearly not a man. And then on the right, a man is walking down the street with a suitcase. So these are sort of image understanding tasks where we want to take an image and from that extract not just the classification, but also the sort of a sentence that kind of represents semantically what's going on. As you can see, each one of these descriptions has an arbitrary amount of words in it, and also kind of conforms to some amount of grammar. And the problem, the reason this doesn't comply very well with our previous approach, right? Imagine that the output space we're trying to map to all possible sentences of 10 words. And so our output space all of a sudden is this very large space, because we have to sort of represent every possible combination of 10 words against a dictionary of some size. So say we don't want to deal with all possible words, but rather we want to deal with a set number of words, even if we were to do it at the character base, right? Say we want to deal with all potential sentences of length of about 10 words, where each word is about, 5 characters. So then we have 500, characters times 26 possible characters. Assume we're only doing lowercase or something, right? So it's a very large output space. And the harder part yet is representing the total possible combinations of that. So for every possible option, we would have to somehow have a sufficient amount of data to represent that case in our model that we're training sufficiently well. So say we want to have about 1,000 examples. Let me do some back of the envelope math here. So in that case, we need at least 1.3 million examples. Say we wanted 1,000 images for every single sentence combination of maximum of 5 characters per word with 10 words. And you can see, and you can kind of hear this is sort of artificial, and not every combination of letters is going to result in a word, but also at the same time, our words aren't only 5 letters long, and some of our sentences are not necessarily going to be only 10 words long. So all in all, it becomes just intractable, in short. So you can technically do this, but you would have to essentially have a dog crosses the street, and you would have to have 10,000 examples of a scene that exactly represents that particular scenario. And as you can kind of hear, that's not a very general approach to this problem either, right? What we want to do is we want to train a network or some kind of system that can determine, oh, there's a street in this image, oh, there's a dog in this image, and contextually, when a animate object is in the middle of a street on this sort of what looks like a crosswalk, that means that they're crossing. And so you can kind of train all of these different sort of semantic behaviors into our model. And so our approach of kind of hard coding this and doing it brute force would not actually result in a representation that is particularly useful. So we may be able to train to our test data, to our training data, but ultimately when we deploy it into real data, and it sees something that doesn't necessarily match up particularly well with any of the examples, say a man is walking across the street, but we don't have any men walking across the street in our data, we only have dogs, then it might not necessarily classify particularly well. So in other words, it's a kind of double-edged problem. It's not really easy to solve in either data coverage, but also in terms of just the tractability of creating a model that is able to deal with this sort of large output space. So what can we do? Well, the solution is what's called a recurrent neural network, and the sort of underlying idea of a recurring neural network is you have a neural network. In this image here, it's represented in this A block, and the neural network outputs a particular hypothesis. So it outputs both a hypothesis or a Y value, and also outputs a activation or a hidden state that is then input to itself in the next time you run it. So it's sort of calling itself over and over again. And if you look at it kind of unrolled, say in this case where we're inputting the word jazz, J-A-Z-Z, you can kind of see that now our data has this additional dimension, which essentially is time. So it's a time step series where now every example in our data set is not just a set of features, right? It's actually a set of features for a particular time step. And now our output is not a particular feature vector or a particular outcome, but rather a feature vector for a particular time step. And there's this additional concept of a hidden state. And something that you don't see in this image here is, but you do in the recurrent example, is the hidden state. When you first start it, you are feeding to the network a sort of initial value for the hidden state, which is just initialized to your sort of liking. But yeah, there's a lot of different arrangements of recurrent neural networks that we'll talk about, but this is sort of the big picture. Honestly, this image here of a network essentially taking an input and outputting some value. This is sort of what we've seen all along, right? We input a value, then it outputs a value. But the additional stage here is that it's outputting a thing that it's then inputting back to itself. And you can kind of intuitively think about this hidden state as a sort of representation of your current state in the data going over this time series. So in a way, right, let's say I'm trying to train this model to learn words, like in this case I'm outputting JAZZ, and I want to convert that into some code or whatever. Right, I may be trying to train it, say, like one thing we'll see in very quickly, by the way. So say I'm trying to train it against a dictionary, and I want the next letter, I want this network to predict the next letter. So in this case, J would be the input, and we'd want H0, the nomenclature here is bad, it should be H1, but we want the first output to be A. And then we would take this output and input it into A here, and then we'd expect this to be Z, and then so on and so forth. That way we kind of have an error, as we'll see in a second. We can say, well, I put in J and I expected A, but I got some other value, and now I can kind of create an error based on that. So, we'll talk a little about how that works in this lecture, but as you can see, this is very powerful for, character-based generators of text and things like that. And in fact, up until recently, recurrent neural networks have been the main way that, well, not the main, but one of the most popular ways that natural language processing was done, because as you can see, it's quite effective at learning these really complex and sort of time-based relationships between things such as words, or even spatially in an image, a dog crossing the street and so on. You can imagine each part of this step sort of outputting a different part of the image, saying dog, street, walk, and then in turn also the hidden states somehow coupling and making a relationship between how those words should be formed. And this is exactly what we see with kind of the more sophisticated recurrent neural networks, for example, like LSTMs. But we'll talk about that more in this lecture in a second. So you might be saying, okay, this is all great and all, but how do we train this thing? Right? It's hard enough to do a backpropagation in terms of a single neural network. How do we do this for the RNN? Well, just like we kind of saw in the previous slide, where you take the recurrent neural network and you kind of unroll it, you can do the exact same thing in terms of training. And the kind of term for this has been nicknamed backpropagation through time. And the reason is you now run your neural network forward, one step at a time through your entire time series of data. And you can do this with multi-batch and all that stuff as well. It's no problem. And now you have all these outputs, and you've hopefully cached all of this information as you've gone for the time series. And now you can do the exact same thing backwards. And because you're essentially taking the gradient of your hidden state and backpropagating it to the prior recurrence of the network. And something that we'll talk about very soon, and we'll talk about more of the mechanics of these systems in a second, but just keep in mind, you are applying the same weight matrix each time you call this neural network. You're calling this, so sometimes you see one weight matrix, often it'll be split up into these two, the WYH and the WXH, and the WHH, which is just sort of I'm not explaining this particular one, but we'll see the mechanics of it in a second. But you would have that same backpropagation of, now we would calculate the loss respective to the weight matrix at a particular time step, and then keep kind of going backwards with it. And so every time you do that, you're going to have an output and a loss, and that loss just gets added in to your prior errors, and you can back propagate that loss as well. So this is a bit more complicated when you have an output at every single time step. Or complex loss. You can use softmax. You can use the regression and like a regression loss, like a Euclidean distance, if you want. It really kind of comes down to the problem that you're thinking about. But in the context of, say, again, like like a character RNN that's trying to predict the next letter in a sequence of letters, often you'll use the softmax loss or the you'd use softmax loss and logits to determine which character should be the character that is output in a particular sequence, and then you can calculate the error against what it's supposed to be, add that to your gradient that you get from the output path, and then combine that with the gradient that you've received from the preceding the step ahead of you. So you're kind of going backwards in a way. Yeah, so I know it's a little bit much. Like I said, we're not going to go super deep into implementing these things. This is like a subject that could take, a whole month for us to go through and implement and go through. So if this is something that you're interested in, please let me know in the Discord. I can put up some assignment, like I could put an assignment together for it. I could try to put together another lecture specifically on the implementation of RNNs. They're very interesting, but just kind of wanted to talk about this, and we'll go into a little bit more technical depth in this lecture, but we're not going to talk so much about implementing backprop through time. We'll talk a little bit about forward propagation, how to do this, and how to use different kinds of RNN topologies, but I'm not going to go into super depth on actually the technical implementation here, so let me know if that's of an interest to anyone, and I will do a bit more, I'll make more material there. So to kind of talk a bit more brass tacks, how do we evaluate, how do we use an RNN? So say we've already trained our RNN, and I've already kind of talked a little bit about this. We basically just run the network. And so if you're using characters, right, you may want to have a character that represents the end of the line. So this is probably pretty familiar to you if you've ever done any kind of file I/O. There's always like an end of line, end of character, end of file kind of character that you can use. And that's kind of how the network knows to stop. If you're using a word, it's the same idea. Again, the network needs to kind of know how to stop, or you can do it for a particular number of times. When we run the RNN at test time or evaluation, we just, it's the same thing as the forward propagation pass, except we don't evaluate the loss function because we have nothing to evaluate. And this is sort of gets a little bit into the how do you do, like what are you trying to do? Like for example, in the bottom you can see we can pass in a girl walked blah blah blah, and this will just output particular values against that. More often you'll see things like the recurrent neural network in evaluation will be called upon itself, and so you put in one word and it'll output the next word, and now you've taken that next word and plug it in as input to the next call. And keep in mind, again, during test, during evaluation, we are still passing that hidden state every single time to ourselves. So that hidden state is being manipulated. You can imagine that, again, if say we're telling a story and that hidden state may be representing where in the story, how many, like the plurality, do we use a plural for the next word or not, given the context, do we use grammar? These kinds of things are largely encoded in the hidden state. And that's what we're trying to train our model to do, is looking at the hidden state, kind of understand what should or should not happen in the next sort of running of this thing, and then how to manipulate that additional hidden state. Now, you might be sort of thinking about this already in the terms of this sort of conditional probability, if you're familiar with this. So one of the things we can think about, and this is more kind of thinking about this from a statistics standpoint, the way we can think about the output is essentially our next hidden state conditioned on the value of our input and previous hidden state, where you start off with a hidden state that's initialized against some kind of distribution, say whatever. It could be 0. That's a great that's a great, very deterministic distribution, or it could be a normal distribution or a uniform distribution. And our initial value of x is going to be pulled from our p data, right, ultimately. And so often you'll use some kind of function, some activation on the RNN to get you your output. And so we're taking say, a sigmoid of the probability distribution of like y now conditioned on the x1 and h0. And so the output on our hidden state is going to be the probability distribution, like is going to represent a probability distribution of this next h given by these parameters of our network conditioned on x1 and h0. But the next one, right, given that we're taking in the next time we're calling our neural network, we're now passing in h1 as, taken from this p theta distribution, and again our x2 is going to be pulled from our distribution of our data, and so you can kind of see that the probability distribution represented by the second output is going to be equal to the probability distribution given by theta of the probability distribution of this, or we're kind of chaining essentially these things together. And so this is sort of a very badly explained and sort of long-winded way of saying that our future predictions are largely conditioned on the prior data that we've seen. And this is an important thing to think about in terms of what these recurrent neural networks are doing, where, say, the 10th word or the 10th piece of data that they're outputting in a way is a product of the data that we've seen thus far, and also the data that we've predicted thus far. And this sort of is a way to think about intuitively or mathematically the way that each incremental call on your data is doing. You're kind of like transforming the data in some unique way, and that transformation is represented by this probability distribution as given by the theta parameters of your recurrent neural network architecture. So this is just kind of a fun way to think about it, which I think is very useful, given that recurrent neural networks and sort of autoregressive models, for example, are kind of the same thing, right? It's really kind of a way to think about the fact that we're calling ourselves on ourselves, and we're using previously conditioned values and the previous conditional probabilities, and we're kind of chaining them together. So if you're familiar with like Bayes nets and things like that, it's a very similar idea. Whoops. Okay, cool. So in terms of actually using these things, we've already seen models that take one-to-one. So you give it one value of x, and it gives you one value of y. With RNNs, now we're able to do one-to-many. So I give you one value of x, and as we've talked about before, the output of y is then used as an input for the next one, and so on and so forth. By the way, that's not actually necessary. We don't necessarily need to use the output for the next input. We could actually not do that, and it'll still work as long as we have some kind of termination y value to know that we should stop doing it, right? We just don't give any input in the next one. There's also the concept of many to one, so we can have an initial activation state, and we pass in a bunch of x values, and on the final value we evaluate y, and only for that. And that's sort of the use case there is, for example, semantic analysis. So say I give you a Yelp review, and I want you to tell me whether or not it's a positive review or a negative review. Maybe I want to take in a bunch of people, I want to make a safe application for children to text message, and this is a way for me to take in a message and determine if it's abusive or if the person's bullying them or not, given I have enough data to determine that. Also, a really classic example of this is spam detection, for example. And then we also have this idea of many to many. So many to many, we've already seen the sort of example of I give in a bunch of inputs and I take a bunch of outputs of the same number. But there's also a way to do this without having an equal number of y's and x's, as shown on the right. And the way that we would do this is sort of we provide a bunch of x's and take no outputs, and then we take a bunch of outputs. And so now we can have a differing number of inputs and a differing number of outputs. This is also known as sequence to sequence, and one of the kind of unique ways to think about this is this sort of encoder-decoder combination. And so you can see here, one of the classic use cases of the sequence-to-sequence application is in what's called machine translation, where you would take in a sentence in a particular language, and then you would encode that into some hidden state of some kind. Don't worry about the embedding lookup. That we're not gonna. I'm not talking about sort of specifically NLP techniques here, but if that's interesting to you all, please let me know. I'm happy to kind of go and shake the rust off of my knowledge there. But often what you're doing is you are encoding. You're not passing the words directly into these architectures. You're actually encoding them using something like word2vec or something that represents a relationship between words and not just the word directly. But then you pass that into, you've now encoded your sentence into some hidden representation that is passed along on the output, and now that's being taken as an input, and you're taking outputs at any given point, and the idea there is that now we're translating this into a different language, and you can kind of imagine that this is necessary because I drink milk is not necessarily the same number of words as I guess it's jeb boy whatever. I don't speak French, but it's a different number of words than we have in English to translate it into a different language. So this is a way to do that. And if you're all interested in NLP techniques like this and how to actually encode this and what does that encoding mean, that's actually an unsupervised technique that I'm happy to go into in the next lecture, in the next series of lectures. So please let me know. So talking about this a bit more kind of hands-on, like how would you build one of these? Well, the vanilla RNN architecture is actually quite simple. As you can see on the right, your function essentially takes in a hidden state and a value of and a feature vector, an input feature vector. You can then treat this as a activation. The output is run through a tanh function, where you can, like as I mentioned, you can split this into two matrices where you have one weight matrix called WHH times the input activation, the input hidden state, plus, and then you add to that the same thing with X. So you can kind of see some of the requirements here in terms of the sizing of your hidden state as well as your X, because if you want to add these two, I mean, they kind of have to be the same respective size to do so, right? Also, the output Y is then a different weight matrix times your hidden state, and that's kind of it. And one of the kind of key distinctions here is that, oh cool, I have a little red dot. That's fun. One of the key distinctions here, as you can see, the output hidden state is the product of the weight matrix of the hidden state times the previous hidden state, whereas the output of Y is actually the weight matrix of HY times the new hidden state. So you actually do this first, and then you do the second thing second, and that way you kind of have it. But like I said, some people, in some places, you'll actually see WHH and WHX concatenated into one, and then it's just H times the concatenation of the previous hidden state and your input feature vectors, and then your output Y is just a weight matrix WY times the new hidden state. But it's largely an implementation choice, so it's not a huge difference. One thing you might be kind of thinking about if you're looking at this here is you see a bunch of these stages chained together, and as you can see here, the output is this weight matrix times this hidden state, and the hidden state is a product of this this matrix multiplication through this nonlinearity. And you can probably already guess the problem, right? We've got this vanishing gradient problem in RNNs because if you follow this path, right, from this say output hidden state through the tanh, you're basically going through this matrix multiplication of W over and over and over again. And as you know, and this is more of a general statement about a number of chained together stages, you start to see that the gradient is just this, the gradient at the initial stages is going to be multiplied by a L number of times. And again, as we talked about in the previous lecture on vanishing gradients, you start to run into this issue where if your weight matrices don't have a norm close to 1, if in fact if they're anywhere above 1 or below 1, you'll either have exploding gradients or vanishing gradients quite rapidly. And so this is a big problem with the vanilla RNN architecture, and as a result of that, RNNs have been, limited to some degree in not necessarily depth, because these are not deep networks. As we talked about, each one of these architectures, each one of these calculations is just one weight matrix multiplication. And by the way, these can also be stacked above. So if your output, each one of these, you can just stack them on top, so you can have deeper RNN architectures. But again, that's a little bit out of the scope of this lecture, and so if there's more interest in that subject, please let me know. But the long story short here is that RNNs have this vanishing gradient problem, and so the solution to this, and this, a whole lecture could be devoted just to LSTMs and GRUs, which I'm not going to do unless that's something that's very much of interest, because I've now implemented backprop on an LSTM enough times to know that I never want to do it again, which maybe that's the homework assignment. I don't know, maybe, we'll see, but probably not, because I'm not going to cover it in lecture. A lot of the frameworks have LSTM gates and GRU gates already, so you can just use them that way. But let's talk a little bit about LSTM. So LSTM stands for long short-term memory, and the key thing to really look at here is this sort of effectively this straight shot path from this output value of C to the input, and also a much more direct way to basically a much more direct path from these output gradients to the input. So one of the things that it might be a little bit easier to see here in the GRU cell, because the GRU cell doesn't have this C value, which I'll talk about in a little bit. But the idea at the high level is with LSTMs and with GRUs is to provide a sort of direct path for the output gradients, or direct flow for the output gradients to the input, and so that way you're not dealing with that accumulation of multiplying the weight matrix at every single stage. You can see this addition here that ensures that, because say at this stage here, ht minus 1, or ht is the nonlinearity of w times this value, and so the derivative of this is essentially going to be, not including the nonlinearity derivative, but essentially is going to be just dw of this current stage. And so you don't have that, you don't have as much of that issue. Let me pause and see if I can find a slightly better resource on this as well. Okay, let me attempt this explanation slightly better this time. So in the case of the LSTM, as you can see, the things affecting the output the things that sort of affect ht minus 1, if we follow this path, we see that it's going through this sigmoid through what's called the forget gate. I'll talk about this concept of gates in a moment as well, but essentially, we've got this forget gate that's being multiplied by this cell state additional thing, and this connects this to the output, also to the next hidden state. So the hidden state output here, not to mention we're outputting it to do something with y up here, don't forget, but it's going up, it's getting multiplied by the C, and then it's getting added to these other things. In addition to that, we are going through the sigmoid of the input gate, the sigmoid of what's called the candidate gate, the tanh of the candidate gate, which are getting multiplied together, that are added, as well as the sigmoid of what's called the output gate, which is multiplied by the tanh of this cell state. And you can see this connection between the next cell state and the previous cell state, and also the next cell state and the H state. And I'm not going to go into super depth here, but the key is that during back propagation, we're not multiplying by W, by this nomenclature here is not particularly good because these are element-wise calculations, and so we are multiplying the weight matrix by the element-wise of the inputs, but one moment, let me find like a slightly better thing. Yeah, sorry, I chose a very bad image to use here, but the point I'm trying to make is that these are actually dot products here, and not matrix multiplications. So the U and the W of the output gate, the forget gate, these are element-wise, these are dot products, not necessarily matrix multiplications, and as a result of that, we actually don't have a W multiplication in the back prop. We do have a element-wise W weight multiplication per, but we do have this direct path from the output gradient to the input gradient without this matrix multiplication in the way. And that allows us to have, to reduce the vanishing gradient problem. And you can see the same thing in the GRU, in the gated recurrent unit architecture. I'm not going to go into too much depth about these gates, but the idea with an LSTM and a GRU, GRU is just kind of, it's funny, like the LSTM cell is pretty old, it's from like 97, and the GRU is a little bit newer, which is surprising when you look at the architecture and you can see, yeah, here in the GRU you can see the dot. That's like the dot product, not the multiplication, which I think in the top example here is very kind of confusing. But the GRU is a little bit newer, and one of the reasons that it's newer is because the goal of the GRU was to try to reduce the amount of computation required in this, because you can imagine back in 97 a lot of this stuff had to be done essentially manually, and that was really painful. But actually these days both LSTMs and GRUs are not seen as much, and are being kind of put down in terms for MLP stuff with transformers, which we may talk about in this course, but they're very interesting ideas where you have this sort of cell, and that cell has a particular state. In the case of the GRU, the state is sort of encoded into the hidden state passed along, and then the LSTM cell, you actually have a unique value called the cell state. And what the cell state is doing is using the sort of combination of gates, is trying to determine whether or not it should forget. So the forget gate, given a particular activation against the forget, some function determines whether or not it should override the cell state with the input. And same thing with the input and the candidate. It kind of does a similar thing where it's trying to calculate what should we have, and whether or not the input justifies that, and so the combination of that determines whether or not it should then sort of add or update update our cell state, and then the output is sort of I'm horribly explaining this. I apologize. This is not. I really just want to kind of make sure we cover the kind of broad strokes here, because as you can hear, this is a deep subject. But let me explain these gates a little bit better than I have been. Okay, let me explain this one at a time, and I think it's going to be a bit better this time. So the forget gate, so keep in mind the sigmoid function is from a value of 0 to 1. So if the sigmoid, and keep in mind each one of these is multiplied by its respective weights, that again are dot product, not matrix activations. And so the sigmoid will determine whether or not we want to forget. So it's going to calculate a value between 0 and 1, and so if it's 0, we multiply the cell state by 0, and it goes to 0, or 1, we're going to maintain the same value, or some amount between that. So it's sort of, allowing us to turn on or off the input. So this is sort of a gate that determines whether the cell state is maintained or forgotten. The input gate kind of does the same idea, except it determines whether or not we want to utilize the candidate value that we've calculated on, and the tan H, keep in mind, is a -1 to 1, and so it allows us to kind of come up with a candidate value, and the input will determine whether or not we want to add that and how much of it to the sort of cell state. So now we have a combination of either our previous value plus some new input candidate values, and maybe we don't, the kind of combination of whether or not we've maintained the previous state and some addition of new state. And then finally, the output gate sort of is a tap on whether or not we want to keep our cell state, that is the output here, how much of that we want to apply to our hidden state. So it might be 0, and in that case, we don't do much. It might be 1, and then we basically pass in our new candidate cell value, and we pass this along. And these sort of set of manipulations allow us to sort of hold on to very long-term dependencies. So for example, in the cell state, imagine we have a bunch of different values. One value could, in theory, represent whether or not a word is plural, or say if the pronoun should be female or male, or these kinds of dependencies. And so we can carry these for a very long time. And keep in mind, the LSTM cell, right? The cell here, the cell's output, the cell state output, and the hidden state are being plugged back into the input here, right, until we get to a termination state. And so this can be rinsed and repeated over and over and over again. The GRU, I won't go into too much depth because the LSTM is, I think, the more interesting concept. The GRU sort of distills this down and simplifies it, where you can kind of see a similar thing going on here, where you have the, again, the output. We determine whether or not we want to apply the input to the output and by how much. And then we decide, we kind of apply the inverse of that. So this is almost like a fake forget gate. This is Z of t value. And similarly here, this is just sort of taking how much of based on the hidden state, how much of that do we want to combine and potentially apply to our output. Again, I haven't done too much with the GRU, but you can sort of see that the update, it sort of determines whether or not and how to manipulate our hidden state based on a variety of different sort of things that are going inside, and these weights that are, by the way, learned, right? So as we're training these networks, these weights are being manipulated and changed and so on based on the output that we expect to see. And so it may seem kind of like magical, but it's really not. It's the same thing as we've been talking about this whole time. And again, one of the big advantages of an LSTM or a GRU cell is that they provide this direct path of the gradient without requiring a full matrix multiplication of the weights, such that we don't have the vanishing gradient problem quite as much. We still do have this dot product of the weights, and so yes, that can still have problems, and that's one of the reasons LSTMs have not been as successful at very large corpuses of text, but more recent architectures have kind of come about to deal with very large text corpuses. It's not to say that you can't apply these things for large things. It's just the problem with the vanishing gradients or exploding gradients is that it's hard to train them. And so I'm, again, not an expert in NLP by any means, and this is kind of the part of machine learning that I have not paid as much attention to as I should have, but and I'm still learning, obviously, like everybody in the space. Just keep in mind these are starting to kind of fall out of fashion a little bit, but are very useful to understand. And so I would recommend this actually as a project. I've implemented these I don't know how many times at this point, yet there's still a little bit of black magic in there for me. So to kind of finish this lecture off a little bit, there's a really great blog post I recommend you all read, titled "The Unreasonable Effectiveness of Recurrent Neural Networks." It just shows in this paper they trained a number of RNNs on different sort of types of text, and you can see, for example, the fake Shakespearean novels or the sonnets that it came up with. But one of the more unique ones that I've really liked is this idea that they trained it on a large corpus of text of latex papers, right? Because latex ultimately kind of breaks down into just a code, and you can train it against the code. In fact, they've trained it on things like C++ code and C and all that, and it actually outputs things like they did it on the Linux kernel, I believe, and it output a bunch of data or a bunch of code that looked like, kernel data, although it didn't compile or do anything, but it was actually pretty interesting. But one of the cool ones is they did it for all these scientific papers, and you can kind of see it kind of comes up with lemmas and these things that don't really make any sense, but if you were to read it, you'd be like, wait a minute, like that x to y prime to y to y to y prime to x with a subscript. It's a very funny one. It looks real until you kind of dig into it. It even comes up with diagrams, because you can draw diagrams with latex as well. And so it's pretty amazing just how effective these architectures are, even though they're not really operating on anything particular. They're essentially just predicting what the next character should be. And so, definitely a very fun thing, and very applicable, by the way, to games, right? In the terms of imagine an AI that you'd like to speak with that can come up with interesting content that's unique and different and not kind of previously scripted. So one of the reasons I really wanted to include this in this seminar is that this might be one of the things that you might want to look at for building your project, or something that actually would be very useful. While these particular architectures are not as popular as, I think, transformers and things like that for NLP, in a more general sense of like ML research and such, they're very effective for, as you saw, the model's quite simple, and you could totally do this in real time in a game. You can just run this RNN over and over again to come up with different things. You could probably imagine doing this for height map generation or complex terrain, because you could do this in 2D with an image, also known as an autoregressive model. And so this is something I'd really recommend you all to check out and kind of dig into it deeper. And if it's something that's of interest, I'm happy to put together a more robust lecture on actually how to implement these things and kind of show some examples of that. So please let me know. So in the next lecture, which will be this week, I'm about to record it again, I'm just splitting this up for convenience. We'll talk about the new unsupervised learning ideas. And we'll start to talk about clustering, dimensionality reduction, and then maximum likelihood models, which will lead us into sort of generative models shortly thereafter. So yeah, excited for that. That'll be a relatively short lecture as compared to this one, so tune in, and we'll see you on the other side. Bye.